Welcome to Data Structures and Applications. This is Dr. S. Nanda continuing my lecture on this particular subject. Now, this session, I will just discuss about the various programs, which means the data structures, which we have already studied, and how to execute the programs corresponding to all these data structures. In fact, we have shown about stack, infix to, suffix or postfix conversion, suffix evaluation, etc. In previous sessions. So I will just dedicate this session only to continue the discussion on the same, but considering other data structures as well. So this is going to be purely on the execution of the programs. So we will limit our discussion only to that, but not, explaining the details of the algorithms or the methodology of various data structures, how they have been designed. For instance, Q, NQ and DQ are the two functions or operations. The concepts behind all this have already been discussed, so we will not waste time on that. So straight away, let me just go to the Visual Studio Code. Let me just share that screen. Yeah, so this is the tool which I'm going to use to demonstrate the working of various data structures, starting with normal Q. You can see here q.cpp. That's the program which has been opened. So quickly we shall go through this program. So the maximum size of the queue is 4. It's limited so that we can show the exceptions like overflow and underflow. So we have two functions here, NQ and DQ. NQ is for adding an element into the queue. DQ is for deleting an element from the queue. So display is a function which actually displays. So the program is written in C bar C++, and again I've explained about Visual Code. So we are using GCC compiler in this and a debugger as well, G++ or CPP. Debugger is actually G++ debugger. So there are a lot of settings which need to be done for Visual Studio Code. For instance, JSON files need to be, I'll just show you that. Yeah, launch.json and task.json. So these two files have to be configured in order to debug, the C++ programs. So there are three functions here which need to be explained as done in the algorithmic point of view. So we have an array called queue which holds the elements. So it's a normal queue and static. So two pointers which are required for operating the queue, front and rear. You can see here both are declared here, F and R. Element to be inserted into the queue is E. So other variables, local variables, which are required in order to show the demonstration of this by, in the form of a menu, like we have insert, delete, display, and exit. So as usual, we just initialize the pointers F and R, F being 0 and R being -1. So before adding any element into the queue, we just increment R and then add the element. So the main function, it's a while loop which keeps displaying the menu every time. And the case 1 is adding. So the function NQ, which actually takes up these items, that means the actual elements to be stored in the queue, and pointers, rear pointer is enough because we need to just increment and then add the element. To be added is E, and this is ampersand because the reference parameter, once we add an element, R is actually incremented so that we can get the latest value of R back to this main program. And similarly, we have case 2 where it's deletion, and we have both F and R which will be returned. So this is a void function, this is a function which returns. So supposing if the DQ returns -1, we know that it's an underflow. That means no element is there. Otherwise, we just delete show that element, deleted element. Display, we need f and r because display is a function which actually displays all the elements starting from element pointed by f and up to the element pointed by r. So that's the total contents of the queue at any point of time. This is for exit. So anything else 1, 2, 3, 4 other than this value, it becomes an illegal entry. Well, so the two functions which are which correspond to the operations of the queue. So the enqueue, enter queue, because we have sent ampersand here, so it's a pointer variable r, an element to be added. So check for the overflow condition. So if r is max -1, it's an overflow. That's understood. Otherwise, you can add the element after incrementing r. So whenever you want to access the pointer variable in C, you have to use star. So that I think you already studied. So increment r and then add the element. So automatically reference parameter r automatically gets updated even in the main program. And when it comes to deletion, again f and r are required. Both might get affected because when there is only one element, that means f and r will be pointing to the same location. You can see here. In which case we can understand that there is only one element in the queue and need to be reset back to the original initialization, that is f equal to 0 and r equal to -1. Otherwise you just increment f. So that's exactly what is done. And underflow condition, as per the literature, what you explained, PPT, this condition is checked. And otherwise, it's not an underflow. So just retrieve the element pointed by F. And resetting is done in case where you have the last element being retrieved. Otherwise, we need to just advance F so that it points to again the filled element, next element in the queue. After this, you return temp. So display is actually this where we have to display from F to R. So we need just a for loop cancel starting from F up to R. So when no elements are there in the queue with this condition F is greater than R, nothing to display. So you can just say queue empty. Remember, empty is different from underflow. Empty happens when it is displayed. Display function is called. Underflow is when DQ, deletion from the queue is called. So that's the basic difference. So now we shall execute this using this debugging command. So I'll get a different window in which I have the first menu. So let me just show first display. No elements are there. Queue is clean. So you can see queue empty. And let's say 2, that is delete, no elements are there, so underflow should come. Yeah, queue underflow message is displayed. Now I'll just add elements, 2 elements I'll just add, 1, 1 and 2, 2. So currently the queue has 2 elements. We can just display and show it. Yeah, 2, 2 is added after 1, 1. So the first one is the front, the last one is the rear of the queue. So let me show how the overflow occurs. So I'll just add some more elements. Yeah. Now there are 4 elements and now I'll try to add one more because the queue size is 4. Yeah, now you can see that it's an overflow because I can't add 5th element into the queue. Now I'll show you deletion. So after deletion of the element which has been added, the first, foremost. As per the FIFO policy, so 1, 1 was the one which was added at the beginning, first one. So that will be deleted first. So you can see again the remaining elements in the queue are 2, 2, 3, 3 and 4, 4. So can I add one more now? Because there is a space actually, but it won't allow because it's a normal queue. So I'll just try to add 9, 9. It will simply say that it's overflow because R is pointing to the max -1. So now display, yeah, now I can keep deleting 2, 2, 3, 3, 4. Now if I try to delete underflow, that's it. Okay, so now it's reset back because all elements are deleted and queue is empty. So now it should be able to add. So 1. So now you can see that 1. So that means when no element are there, that all elements have been deleted, and will reset the pointers so that it acts fresh queue. Okay, so this is the working of the normal queue. So let me just go to now circular queue. Right, so you can see here the circular queue, again enter, delete and display. So in this case we use formulas for addressing f and r, and initialization f equal to 0, r equal to 0. So this is different from the normal queue, and the menu of course remains same. The only change we require is the calculation of the pointer values f and r. So in this case entering, we check for the overflow case, otherwise we will just calculate the real value. It's not r equal to r plus 1. So we calculate using the mod function max, as we already said, because it should work on a wraparound fashion. So once we calculate the address of, then we can push this E, that means element to be added to the queue pointed by R. Similarly, deletion, check for underflow, else calculate the value of F using this formula again and store this in temporary and return that, or you can simply say return. So that means entering and deletion happens here. Now display, of course, because it's in a circular fashion, so we cannot display like F to R, right? So when F and R are the same values, 0 actually, we say that it is empty, nothing is there. Now, otherwise, we have to we have to display all the elements starting from the current value pointed by I. So that address we can calculate using again mod, because F also takes over R and it keeps rotating. It's a circular one, and hence we need to calculate that. So calculate this address and print that value, and next time when it goes to the while loop, then again calculate the next address. For instance, it could be 2, then 2 plus 1 3. So as long as it's within the limit of the max, it will try to print the current value pointed by I. So this can be repeated until it reaches the R. So it can even go on a wraparound fashion. So that's why we have this formula being calculated. We cannot say that there is an end here. There is no end. Whenever it is circular, there is no end. There is no starting, there is no ending, because it's a circular fashion. So let me just execute this and show you the working of this circular queue. Yeah, now this is my circular queue. The menu is same. Now we should demonstrate that even if I delete, I'll have some space, that space should be utilized. Okay, so let me just demonstrate that. 1 1 3 3 4 4 now 5 5. It's overflow, just similar to the previous one. But supposing if I delete an element from this circular queue now, like say 11 is deleted, now I have space because I have 3 elements, 1 space is there, I should be able to add now. Okay, so I'll just try to add 99. See, now it's accepting. Now you can see that 99 is the last element added, which is after 44, and all locations are utilized. So now I can show 2 2 2 3 3 4 4 and 19. It's empty now. I can reuse it. So circular queue is better than normal queue for the simple reason that we can utilize the space whatever is available in the circular queue, unlike normal queue. Okay, so now we shall take up The third one, circular queue with dynamic variables. So we have this now. So whenever it is full, we should be able to, uh, you know, allocate memory dynamically, and then the element should be added. It's not limited to 4 or 5 like static. Okay, so we have a structure here for the element. So I just have one member here, so you can have an object kind of thing. You can add any more, any number of members here. And so this is not just an integer this time, so it is an object kind of environment. So it is a structure variable, so element. So that is my queue now, and adding into the queue and deletion from the queue. And I have a function called queueFull, which actually takes care of allocating dynamically and extending the memory whenever it's full, queue is full. So that's why we have demonstrated even in the stack case, dynamic capacity is 1, and increase the capacity, doubling all that. So I'll show you that function. So now the because it's a circular queue, so I just initialize f and r to 0. Now coming straight away to this, so the only difference between the circular queue normal and the dynamic one is the queue full. No, it's not overflow. So queue full will be called. So when f is equal to this, we normally say that it is full, but now we call a function so that we get more space. So it goes to this function. So this is the function. Now we have seen that copying work has to be done twice. I think you can recall the PPT slides corresponding to this. You have to actually adjust the pointers after making 2 copies. You can see here, this is the 2 copying from the original one by allocating temporary memory locations. That's a new queue you can see here. So the memory is obtained using malloc by doubling the capacity, 2 into capacity, the size of the queue. So we get a pointer of the type element, so that new queue now will point to the memory being allocated newly or dynamically. And once you do this copying, adjust the pointers f and r, and next time, capacity will be doubled. Okay, so any temporary dynamically allocated variable should be freed for avoiding dangling reference, etc. So that's the statement freeing of this. And once you get this memory, now I can actually add an element E after getting the address for R, new address for R. So the address adjustments have been done using queueFull. So I don't declare it as overflow and wind it up, but we just get the memory allocated and add the element. Underflow, that means in the delete queue, same thing. So no, not much of changes here. Display almost same, except that max we use the capacity, because capacity keeps changing every time when the queue becomes full. I think we can execute this. It will work. OK, let me just do that for you. So I should be able to add any number of elements. So 1, so I have now 6 elements. So 7th one, 8th one, 9th one. So any number of elements, because dynamically I keep getting my malloc because of malloc, and hence I think deletion also you can show the same way because it should work, and hence not making any restriction on the number of elements that you could add into the circular queue. So dynamically I can get the memory being allocated. Right, so now we shall move on to the next program, priority queue. So again, in priority queue, we use one pointer called index, initialize to -1 before adding an element, increment index and add. And ascending priority queue, descending priority queue, that is also called as min heap and max heap, that you will study later. Extracting the minimum element in the given set of elements. Max heap actually extract the maximum element from the given set of elements. Okay. So here the menu is same, except that you need to add or enter into the priority queue. So the overflow is, it should not go beyond it. It's not circular, so it's flat. So max -1 is the normal checking. And if this condition is false, we just increment index and then add. Something like stack where you increment top and then add. Okay, now deletion is a bit tricky because we need to find out the max or min and swap, all that you can recall. So you can see here that the underflow case is that when index equal to -1, no elements are there in the priority queue. Okay, so K is the current max position or the largest element position, and if you find after going through from the second element onwards, if anything greater than this, you save that position. Okay, so that's why you can see here 1 to up to index, up to the end or current index, because index also keeps changing. So if the element pointed by I is greater than the element pointed by K, so 1 and 0, the first element being pointed by I is nothing but first element, means actually second element, index is 1, and element being pointed by K is the 0th element, current maximum. Okay, so if this first element is greater than the 0th element, you save that position. Else you go to the second element, that is I equal to 2. Again compare with the current max, etc. I think this is a very simple for loop which you would have already written to find max or min in your fundamental programming. Right, so once you get the position of the biggest or the largest element, then we can actually swap it with the element pointed by index. You can see here. Before that, I just save it in the temp because I need to return this. So swapping is done and index is decremented because now that the element is gone. Recall again our diagram and you return temp. So deletion is actually based on priority, not first come first served. So we need to find the largest one because largest one is the highest priority, and swap with the last element pointed index actually and decrement index so that we get the balance elements in the priority queue and return the temp, which is the largest one. Display, of course, is very simple, that you just start from 0 to index, up to index, inclusive of index. So that is your priority key. So we shall just execute this. I'll just add elements at random. So insert, because so currently I have 34, 23, 9 and 4. Maybe I'll just add one more, 25. It's overflow because I've just limited to only these many. So currently I'll just delete. Okay, now 34 is deleted because that is the largest. So now which element should be deleted? It is 23 because the highest priority among all these three is actually 23. So that should be deleted. You can see there. So the balance elements are 4 and 9. Now 9 is the largest. So next priority goes to that. So it's deleted. So among the elements available, the largest one is found and deleted from the priority queue. So deletion is based upon value where the larger, the higher the priority. Okay, now we shall move on to the next program. Fifth one, multiple stacks. Right. So multiple stacks, it's almost similar to the single stack program, but here we need stack ID. That's very important. And we also require arrays for top and bottom. So items, it's okay, same now as usual. So maximum memory and maximum number of stacks. So maximum memory divided by maximum number of stacks will give me the number of stacks which I can maintain. For example, if max memory is 15 and maximum number of stack is 5, as we discussed already, 15 by 5, 3 elements will be the maximum size for each stack. Okay, so we need arrays for both the top and bottom, because for each stack we need a top and bottom. So the stack ID is very important. So you can see here there is a variable which is maintained for that. Otherwise, it's very simple. Okay, and initialization has to be done as again we have demonstrated. Shown earlier. So top of 0, 0th stack is -1. Remember that stack ID starts from 0. So 0th stack is the first one. Starting from first stack, we can just initialize both top and bottom pointers. Okay, now this is main program as usual. Now we will concentrate on push and pop. So the exception cases of overflow is nothing but, you can recall the diagram where the current stack ID, that top is equal to the next stack's bottom. That means it is, overflow because it has grown that much. Else you can just add the element to that ID, top of I. So I stack. So you can see here the parameter being passed to the push, because I have kept items and this one global variable. You can see items is good. That also can be passed as a parameter, but to reduce the number of parameters here, that is shown as a global variable. So here the I indicate the stack ID. So you can see here that whenever you want to push the element into the stack, now you first get the stack ID, which stack you want to push the element. So supposing if the user gives a legal value for the stack ID, you can just say that illegal. Otherwise, you can pop or push, here, pop or push, anything. So both for push and pop, we need the stack ID, because you have to know from which stack you have to delete or which stack you need to push the element. So here top of I is nothing but top of that stack, because top is an array, bottom is an array, etc. So items is an array where the item value, it's added or pushed after incrementing the ith stack top pointer. Similarly, before deletion, check for the underflow. So this is underflow, and decrement, of course, after retrieving the element. This is a post decrement. You can see is a pre-increment, because push is increment top and then add. Popping is you can pop and then decrement. It's a post. So this one displays very simple from top to top of I plus 1 stack ID, because it top pointer actually is normally positioned one below. Okay, so it displays this, but the stack empty case is this condition, that is top of any stack. Supposing if it's equal to bottom of I, as per the diagram, you can say that it's empty, but otherwise it's top to bottom. It's very simple, top to bottom. Right. So we have 3 important arrays: top, bottom, and items. Items to store, bottom to bottom pointer for each stack. Top is top pointer for each stack. So let us just execute this and show how this multiple stack really works. Okay, first one is you can have any number of stacks. So I'll just say total stacks to be create, say, okay, 3 let's take. And stack ID. So supposing if I give some 8, you can see the stack ID is illegal. Supposing if I give valid 1, this for insertion, that is push. So I'll just give 0th stack and followed by the element. So 1 1, or let's say yeah, 1 1. And again push. This time I'll give stack ID 1 and 2 2. Stack ID 2, then 3 3. So now display stack ID 0, that's 1 1. 3 stack ID 1 2 2, can see there. Again display stack ID 2, it should be 3 3. So it's there, right? So we can easily pop. Again stack ID need to be given. Let's take 2. So 3 3 will be popped, can see there. And I try to pop from the same underflow because no elements are there. So every time when you want to add an element, I mean push an element, you just give the stack ID in the element to be pushed. Whenever you want to delete an element, you need a stack ID and then just leave it, you will get the element popped. So this works fine for multiple stacks. Similarly, we have multiple queues. So this is almost same as this, you can see here, except that entering and deletion is based upon the queue. Enter into the queue and delete. Normal queue, not circular queue, normal queue. Okay, so now we have maze problem. So let me just skip that, execution. This is very important here. This again, you need to recall our earlier discussion. The coding is done based on the concepts of the positioning of the rat and next row and column to be determined for the rat movement, and the direction and the movement, the values for horizontal and the vertical one will be calculated based upon starting from 0, that is north, and rest of the directions. Okay, so we have the entry point for, it's all fixed now, it's defined. So entry point for the rat, starting row and column is 1 1, and the board size I just taken as 6 by 6 array, and exit point for the rat is actually 6 6. So bottom right corner, top left corner for the entry. So this is your vertical and horizontal, that's offsets for the movement, and this is the row column and the direction, that is element. So you have to use stack here. So we have push and pop functions, because you need to remember, coming back, if suppose you end with the dead end, then you have to come back. So pop the latest address so that you can opt for some other directions. So we need 2 while loops. I'll come to that. Before that, this I have fixed the board, like 0 indicates the opening, 1 indicates the closure or the wall. So you can see here the answer is very much evident. 0, if its starting point is this, so it actually comes like this, like this, like this, like this, something like this. So some diagonal, some horizontal, some vertical, like up, north, all that. Well, these are some initialization for the stack and offset movement. I think this is a lookup table. And next row and next column, these are the 2 variables required to calculate. And the current position of the rat is fixed as row column direction. You can see here -1 for north. So we start from there. Okay, now so while, yeah, this is the 2 while loops which I had mentioned. So maze, the structure, sorry, the array is maximum row minus 1 column, that is 6 minus 1 5 and again 5 by 5. So which is 3 by 3, sorry, 5 by 5 array. It's okay. So now we have two while loops. So this while loop outer one is that stack should not contain any elements. That means supposing if you have pushed some addresses and you want to try all those things, so you should be able to do that by using this top. So as long as top is not equal to -1, that means you have some elements in the stack, so you can keep going because we already pushed some elements. You can see here the current position of the rat. So something will be there. Obviously, it will allow me to enter into the while loop. And if I've tried all the possibilities, then this will no longer be true and it will get exited. Now the inner while loop is used in order to try all the directions because, for example, north, when you want to try, it could have a 1. It might be 1, in which case you have to try for the next direction, that is 1. So directional, this one, dot, that is current position of the cursor of the directions may have to be tried for all 8 directions, 0 to 7, and hence this while loop will do that job. And next row, next column will determine movement of the next position of the rat, and it will, as per the method which we have already explained in the PPT, so it will try to find out whether there is some possibility of for the rat to move, provided there is a 0, because 1 indicates that it is a wall, so that it cannot move. Now if it cannot move, then it has to be pushed for that particular address. Otherwise you just take to the next position, and you have to also check whether you have reached to the exit point or not. Okay, exit point or not. So, and another important point is that all legitimate movement of the rat is to be shown as an output, right? So how do we show that? We just put star for the movement of the rat. Now otherwise it is 0. So we have some conventions used here. I'll just show you the output, then you'll come to know. So we have the numbering here, that 3 means that it is a legitimate movement for the rat for the next position. So put a star here. That's why you can see here we have altered the maze information itself, that it is 3. So I'm going to just print maze itself as an array, but this array will now hold star or 0 kind of thing. So star means it's the movement, 0 means it's not. So the entire path can be actually shown as an output. Maybe when I execute, you'll understand. But there are possibilities that there may not be any exit path for the rat from the given starting position, because all could be ones, for instance, all may be a wall. So in which case you should also print that there is no path. So you can see here there's no path if you have tried all possibilities. So at the end of each of this loop, you try for directions. So next direction. So you started with say 0, current, then you can try with 0, 1, 2 and so on. And the outer while loop, you can try the row column as the next one, so that as long as the stack is not empty, you can keep going. Okay, push and pop are the two functions as part of the stack. So let me just execute this for the given board or the maze position. So you can see here that there exists a path, and the path is shown using star. Remaining locations are not affected, this original value. So the starting point of the rat is here. So it can take, these are all zeros actually, as per the program, means the input. So it can come like this, like this, like this. It has gone like this. Now you can see here, there's a diagonal movement, right? Now instead of coming, it could have come like this only, but it has gone like this because we always try from here, north. So when it was here, for instance, it has seen like this is one, this is one, this has already been tried, say this left is one, like that, right is one, this also is one, etc. So it keeps trying this way, directions, and if it finds a path, it will simply take. So that's why it has gone here, and it has found that all these three are ones, and there is a zero here, and hence it has taken, not necessary to try the rest. So it will come here now. It will again start from here. Since this is one, so it cannot move, and hence it goes to the diagonal one. So you can see here it has gone, and all these are zeros, so it has come here. So don't think that it is an optimal solution. It's not an optimal solution because we have a fixed way of trying out all directions starting from a particular direction. So we don't know where the zero is. So when you get a zero, probably it can take that as my next row and column. So still it has found the path. So the stars indicate the row and column values for the movement, and it can exist. Exit. And you can try it all once, and it will not be able to show you any path. So that is okay. I'll just close this. Yeah, that's the working of maze problem. Well, I think these are the topics which we have discussed, and the rest of the data structures are already shown in the previous PPT. And each and every function is coded, the entire program, of course, is coded in C bar C++, mainly scanf, printf all used. And even in the exam, if functions are asked or the programming is asked, easily you can use this. And I'll be able to share these programs, of course, through VTU e-learning portal, and you'll be able to download this code and execute, provided you have a proper editor. So I advise Visual Studio Code is a free, tool which is available from Microsoft. You can download. Only thing is that you need to, configure these things in JSON file of launch and tasks appropriately by downloading some more, programs or the compilers like, GCC or G++, debuggers, etc. And you can get them, the extensions, for instance. These are the extensions. You can install whichever is required. For example, for C or C++, the debugging kind of thing, we need this. So you can see when I click this, you can see it's already installed. Otherwise, so you can only uninstall. Since it's already installed, there's no need to do anything. So like this, Visual Studio Code actually works on the basis of these extensions and additional compilers which you have to download from some other website, etc., etc. So that I think you can Google it and you'll be able to get. So thanks for watching my lecture on the application programs of various data structures. All these programs have been shown using Visual Studio Code. However, it runs on any good compiler, C bar, C++. Thank you.